Hi everybody, today we're looking at part B of lesson 2 and we're going to be analyzing graphs of parent functions. So for this lesson, the first 2 pages will be your notes and then the second 2 pages will be all practice. So you want to make sure you really write down everything and absorb everything I'm saying on these first 2 pages. So we're talking about continuity first. A function is continuous when its graph is a single unbroken curve. And that unbroken curve you can draw without ever lifting your pencil. If you have to lift your pencil off the page, it's not continuous. So I have an example of a continuous graph. Okay, right? You never have to lift your pencil off this graph to follow it along. Then right in the middle, we have a not continuous. We also say discontinuous, all right? And for this graph, you'd have to lift your pencil to get to the next part of the graph. And another example of a discontinuous graph, you would have to lift your pencil off the paper to draw this graph. Right? Easiest way to explain continuity. Next up is intervals of increase and decrease. A function is increasing on an interval if the function values increase as the input values increase within that interval. The average rate of change will be positive. So the slope, right, the average rate of change will be positive. A function is decreasing on an interval if the function values decrease. As the input values increase over the interval, the average rate of change, the slope, will be negative. And I have an example here. So the slope right here up until we get to -2 is increasing. Then the slope from -2 to 2 is decreasing. And then the slope is positive from +2 to infinity, so that's increasing. Intercepts, also known as zeros. So we would find the x-intercepts by setting the function equal to 0 and solving it. Or you can use your calculator. You would go to second trace and you would look for the 0. Or we could be talking about the y-intercept, and in that case, you would substitute 0 in for x. Extrema refers to maximum and minimum. So we're going to be asked to identify extrema. Sometimes you need to use your calculator to do that. It's not falling exactly on your graph so that you can read it. The maximum, of course, is the largest value on the graph. The minimum is the smallest value on the graph. In the calculator, you would go to second trace, either 3 or 4 to get minimum and maximum. Asymptotes. Okay, so we have both horizontal and vertical asymptotes. An asymptote is a line that a graph approaches without touching. Talked a little bit about asymptotes here and there. The following graph has a horizontal asymptote equal to 3. So if we were to draw just sort of a dashed line here, you would see that graph is approaching it, but never quite touching it. The second graph on the page here has a vertical asymptote at x equals 3. Okay, vertical asymptotes are always x equals. Horizontal asymptotes are always y equals. One reason asymptotes occur is because we are working with a rational function. So we have a fraction with polynomials in the numerator and the denominator. Right, so the question would be, how do you find a vertical asymptote? You're going to set the denominator equal to 0 and solve. Right? If we don't have a denominator, we don't have a vertical asymptote. Right? And vertical asymptotes are always x equals a value. So in our example here, if you set x plus 2 equal to 0, you get x equals -2. So we have a vertical asymptote right there at x equals -2. Now, finding horizontal asymptotes is a little trickier, all right? This is really more of a coming attractions for next year. I'm just kind of like letting you know how it works. We're going to keep these very, very basic for our purposes, but I just wanted you to understand, pretty much how it all works. So when we're talking about a horizontal asymptote, we're comparing the degrees of the numerator and the denominator, all right? So if we look at this first guy, now you're going to be saying to me, what is the degree of the numerator? Well, remember the degree is the exponent, of the greatest term in either the numerator or the denominator. So let's see here. You could think of this as having a term of x to the 0. Anything to the 0 power is 1. So the degree of the numerator is 0, and the degree of the denominator is 1. So 0 is less than 1. If 0 is less than 1, if the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote at y equals 0. So right here, let me do that in a highlighted guy. Let's do this. We've got a horizontal asymptote at y equals 0. Now, if we look at the next one, the degree of the numerator is 1 and the degree of the denominator is 1. So those degrees are equal. If the degrees are equal, we're going to take the coefficient in front of those terms, and that is going to be our horizontal asymptote. So in this case, we have a horizontal asymptote at y equals 2/3. So right about here is our horizontal asymptote. And the last one says that if the degree of the numerator is greater than the degree of the denominator, then we don't have a horizontal asymptote at all. No horizontal asymptote. So if we look at this guy, the degree of the numerator is 2, and the degree of the denominator is 1. 2 is greater than 1, obviously. So we do not have a horizontal asymptote at all. All right, so want to keep those pages handy, maybe even separate them out from your notes if you happen to staple it all together. I would keep those separate as we work through these. So for the practice, you're being asked to analyze each graph below. Use interval notation when identifying intervals of increase and decrease and domain and range. Round all values to the nearest hundredth. So the first question is the graph continuous? Now remember, we said that if you don't have to lift your pencil off the page, then we know that the graph is continuous. And we never have to lift our pencil off the page. So the answer to the first question is yes. Intervals of increase and decrease. All right, so we want to see where the graph has a positive slope. And if you notice, if we were to kind of look at the slope throughout this graph, right, that's a positive slope and that has a positive slope. And there's nowhere on this graph where we have a negative slope. So for this graph, the intervals of increase are the entire graph. So we're going to say that that means all real numbers. Over the entire graph, we're increasing. And nowhere in the graph are we decreasing. So we're just going to write none for intervals of decrease. Now the domain is referring to, and you may want to go back and review what we did in lesson 1A. We talked about the domain, what x values are included. And over time for this graph, all x values are included. So that's going to be all real numbers. The range is going to be referring to all the possible y values. And again, because we have all y values included, all real numbers. Now, the minimum would mean the least value in this graph, and the maximum would mean the largest value in the graph. And we don't have a minimum or a maximum. We have, a graph that is going to, negative and positive infinity, and we don't have any absolute large values or absolute low values in this graph. So for both of these, the answer is none. And go back and look at the definitions of minimum and maximum if that is confusing to you. A vertical asymptote, well, we don't have a rational function, so we do not have a vertical asymptote. And we do not have a horizontal asymptote. There aren't any. The x-intercept and the y-intercept happen at the same place. It's always going to be a coordinate. When we talk about intercepts, you always want to write it as a coordinate. The end behavior, so the end behavior as x goes to the left or as x goes to the right, which way is it pointing? So as x goes to the left, we're pointing down. So that means that we are approaching negative infinity. As x goes to the right, we're pointing up. So that means we're approaching positive infinity. And lastly, you're just viewing the graph and identifying symmetry, even, odd, or neither. So if it reflects over the y-axis, it would be even. If it reflects about the origin, it would be odd. Otherwise, it's just neither. And this graph reflects about the origin. So let me show you how that happens. So first we reflect over the y-axis. And then we reflect over the x-axis. And when we reflect over the x-axis, we end up with exactly the same graph. And that's how we know it reflects over the origin. And that's how we know that this function is odd. All right, what you may want to do is pause the video, try to do numbers 2, 3, and 4 on your own, and then come back and watch what I have to say about those graphs. All right, now, I also did tell you, not only just give you the picture of the graph, but I gave you what the graph value is so you could enter it in your calculator. So consider doing that too if you need to. All right, let's take a look at number 2, y equals 1 over x. All right, so is this graph continuous? Well, you can see that when I draw this graph, I do have to lift my pencil off the paper, so this graph is not continuous. So we're just going to say no. We want to know what are the intervals of increase and decrease. So we're looking at the slope. That's really important to note here because these can get a little confusing, right? The slope here is negative. The slope here is negative, the slope here is negative, 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 right? So this entire graph is decreasing, and we have no intervals of increase. So let's just say none here. But you have to be careful when we talk about these intervals of decrease. Over the entire graph, we're decreasing, but we're not including the value of 0 here because 0 is undefined in this graph, right? 1 over 0 is a big math explosion. Not allowed to do that. Not allowed to have 0 in the denominator. So our intervals of decrease are going to include all real numbers except 0. So from negative infinity to 0, and the other interval is from 0 to positive infinity. Notice we're using parentheses next to 0 and not brackets because we don't want to include the 0. All right, now same with the domain, all right? The domain looks like it has all the x values included except for 0. So here's how we would write the domain. Pretty much like we would write the intervals of decrease. We just want to use that union symbol here. And we're good to go. The range also has a horizontal asymptote at 0. So we're not including 0 as we look at this going up and down, right? We're not ever touching the x-axis. So we're not including the value of y equals 0. So we are going to have So for our range, it's going to look the same as the way we wrote the domain. Just doesn't include 0. All right, this is a little bit of a tricky question now, minimum and maximum, right? The minimum is going to be the least value on the graph. And you might sort of want to say, gee, I think that this is a minimum here, because that's where the graph sort of hits a low point. But there are other values on this graph that are less than that. So this guy cannot be a minimum. And you might want to say, oh, this looks like a maximum. This is a high point, but we have many other higher points than that in this graph. So this guy is not a maximum. So therefore, we do not have a minimum or a maximum on this graph. The vertical asymptotes we have a rational function can be found by looking at the zeros of the denominator. Well, the denominator, if we set that equal to 0, boom, we have our vertical asymptote. So we could just sort of draw that in. And we've already noticed that because we've already identified that in our domain. And a horizontal asymptote, we look at the degrees of the numerator. So in this case, we've got x to the 0 over x to the 1, right? Because this is really an imaginary x to the 0. Anything to the 0 power is 1. And so our degree of our numerator is less than our degree of our denominator. I'll just make a note, n is less than m. So y equals 0. So we have a horizontal asymptote at y equals 0. All right, the horizontal asymptote will match up with what you said for the range. The vertical asymptote will match up with what you said for the domain, right? If we have a vertical asymptote at x equals 0, then our domain is not going to include 0. If we have a horizontal asymptote at y equals 0, then our range is not going to include 0. We clearly have no x-intercept or y-intercept, so that's easy. I'm not touching the x-axis or the y-axis. And lastly, we want to look at the graph, how it behaves as we go left or as we go right. Right? On this graph, as we go to the left, we are approaching the value of 0. We're getting closer and closer to 0. When we follow this graph to the right, we are also getting closer and closer to the value of 0. Not infinity, we're getting closer and closer to 0. Identify any symmetry. Are we reflecting over the y-axis to make it even, reflecting about the origin to make it odd, or neither? Well, it should be odd. So if we reflect over the y-axis, it would look like this, right? And then if we reflect again over the x-axis, we're going to be right back where we started. So we know that this function is odd. We reflect about the origin. All right, for number 3, we're looking at 2x cubed minus 6x squared plus 3. And we want to determine, is it continuous? Well, I don't have to lift my pencil. So yes, this graph is continuous. Intervals of increase and decrease, where is the slope positive? All right, so the slope is positive from here, looks like to 0, and then from 2 to positive infinity. So we're going from negative infinity to 0, and another interval of increase occurs from 2 to 0. And then from 0 to 2, we've got an interval of decrease. Our slope is decreasing. So we have an interval of decrease from 0 to 2. What values are included in the domain? So it looks like everybody is included. So that's all real numbers. What values are included in the range? Also all real numbers. The minimum and the maximum. All right, so we could just look at this graph and find that. Here's our maximum. We've got a value of 0.3. Oops. We've got a maximum value of 0.3. And we have a minimum value of 2.5. Now, if you want to confirm that, we'll put it into our calculator just to practice. All right, so we're going to enter the function into y equals, do zoom 6. We're going to find, let's practice finding the maximum. So we're going to go to second trace. We're going to pick number 4. Move your little spider a little to the left, hit enter. It says right bound, so move your little spider a little to the right. When it says guess, hit enter. And it gives you the maximum. Now you'll see that this says 1.46 e to the negative 6. That means move that decimal to the left 6 places. So that means this number is 0.000001, which is basically 0. So we have a maximum at 0.3. We confirmed it. A vertical asymptote, we do not have a rational function, so this would be none. Horizontal asymptote, none. We have a lot of x-intercepts there. We have 3. And they're not falling perfectly on the crossways of the graph, so we need to use our calculator to find those. We're going to pick the 0. We're going to move it a little to the left, hit enter, a little to the right, hit enter, and guess. And so we have a 0 at negative, looks like 0.64. We're going to have 3 here, so we've got to make a little bit of room. Negative 0.64, 0. We're going to have another one. Let's do that together. Second trace, number 2. We're going to move our spider to the left. Now, to the left of this 0 is going to be just a little bit above the x-axis. To the right is going to be below, and hit enter. And we get 0.83. All right, and one more. Second trace, number 2. We have to be to the left for this last 0. That means being below the x-axis. Above it means to be on the right. You're going to be a little bit above it, and hit enter. And that value you get is 2.81. 2.810. The y-intercept, there's no calculator function for that. We could actually just put into the function, put 0 in for x, and what do you get? If you put 0 in for this function right here, it'll tell you your intercept, and you would get a 0.3. And you can see that by looking at the graph. As x approaches negative infinity, we're pointing down, so that's negative infinity. As x approaches positive infinity, goes to the right, we're pointing up, so that's positive infinity. And this graph has no symmetry, so we're going to write neither. Okay, last one, number 4. Is this graph continuous? Well, I do have to lift my pencil off the paper, so this graph is not continuous. Intervals of increase and decrease. Okay, where is the graph increasing? If we look at the slope, we got negative, 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 negative. There are no intervals of decrease. So this is of increase rather. So this is none. Intervals of decrease happen throughout the graph, but you can see that right here, all right, we have a vertical asymptote at x equals 3. So our intervals of decrease are happening up to 3 and then after 3. So from negative infinity to 3, and then we have another interval of decrease from 3 to positive infinity. Our domain, right, is going to be everything but 3, because 3 isn't part of our solution. And our range, it looks like we have, by examining this graph, right, we have a horizontal asymptote at y equals 0, and we'll confirm that in a second. But so when we go up and down on the graph, we're including all the numbers except for 0. All right, we have no minimum and maximum. We have no least value, and we have no greatest value. And that is similar to number 2. The vertical asymptote is the 0 of the denominator, right? So x minus 3 equals 0. So we have a vertical asymptote at x equals 3. If we solve that equation, we get x equals 3. And we've already shown that on our graph. The horizontal asymptote compares the degree of the numerator to the degree of the denominator. So we essentially have x to the 0 over x to the first, right? So that's n is less than m. And in that case, we know we have a horizontal asymptote at y equals 0, which we have already observed. In the case of the x-intercept, there is none, right? We're not crossing the x-axis at all. Right? In the case of the y-intercept, we would put 0 in for x. So let's just do that. If we put 0 in for x, we're going to get, so we have a y-intercept at 0, negative 1/3. As we look at this graph going left, we're getting closer and closer to 0. As we look at this graph going right, we are getting closer and closer to 0. And this graph has no symmetry, so we are going to say neither. All right, so I would say keep those first 2 pages handy. We're going to be doing a lot of practice on these. Hopefully this helps. Thanks for watching.